extend this idea of arc length to be more than just the side of a circle, right? I should be able to extend it to any R, whatever R is, and it looks like who knows what. I should be able to figure out the length of this curve from this point to this point, whatever. You guys kind of with me? Because a circle is just the most basic shape that I could use polar coordinates for, but I can have other shapes that I can find. I should be able to find the arc length for them too. So I'm almost certain I did talk about this. In fact, let me make that 100% sure I did, because I remember talking about if I go from here, let's do something close to there, I get this little tiny triangle, and if I blow that up, this piece was dy, and this piece was dx. It's crazy. So how much did it actually change by?
dy squared.
So we'll call this d, well,
dt.
I can't remember what letter they use.
dt.
Yeah. So what would this be in terms of these?
The square root of dy squared plus dx squared.
Yeah, dy squared plus dx squared. And just to make this, let me actually kind of let me see if you guys are cool with this. Let me make this 1 here, so that means I divide everything by dt. Is that cool?
Oh, okay.
Right? Is that cool? So then I get dy dt squared plus dx dt squared. Square rooted would be the length.
But I have a question.
No. I'm sorry. Integrate. Thank you. So better.
I was going to ask, why is the dt squared 2?
Why wouldn't it be? Because what do I use to figure out what is?
Okay, I got it.
All right. So this would be a little. Let me make this a little more official. That's a little dl element, right? Little delta L element. Let me see if you guys are with me. Yeah. So if I just move from here to here, I've moved by dl amount. And what is dl in terms of dy? It's dx squared over dt, dy over dt squared. That thing square rooted. So if I add all of those little pieces up, I'm going to end up with L. So we did talk about this. I talked about it, I think, about that quickly, because it's not a huge focus of mine. Because actually it's relatively simple. It makes beautiful sense if you let it. I mean, there's not a lot to it. And I just got to plug and chug. Now, the integrals can get pretty ugly pretty quickly because I got a big-ass square root sitting there, and basically that makes almost any integral way worse than it could have been otherwise. Right? You guys still with me? But this is on page 649. They got the little formula there. They basically explain it almost the same way. They just don't identify this shape. That I think really ties it all together. It's just Pythagorean theorem used on the little infinitesimal pieces. And then you integrate it to add all those up. You end up with the whole line. I like it. So it's kind of nice. If I have something just laying straight, I can find out how long it is by putting a freaking meter stick, bam, or a yardstick, depending on what country you're in, bam, right? I can see how long it is. But if I had something like coiling around or something, maybe a snake. I don't know if you guys have seen this. There's supposed to be a giant snake, and you want to see how long is that thing? Well, I can just figure out an equation and then do this. You wouldn't, but I could. Figure out an equation and see how long that snake is using this formula. You with me?
The limits will be t, right?
Yeah, whatever. It's based on t. I like it. Cool. Yes?
Why is the dy over dt or dx over dt?
Just do it one more time, sir.
Why is it over dt? The length?
Oh yeah, this should be dl dt. Because what is this? This is a change in y as t changes. That side. Right, so I kind of introduced it a different way. I said we can make it all determined by dt, and then we can divide and so forth.
Yeah.
But better than that is this is going to be how. In fact, do you remember the whole thing about a car is going 40 mile an hour north? This is 40 mile an hour and it's going 50 mile an hour east or something. This is actually going to be dy dt. This is actually going to be dx dt. So how quickly? Let's say there's one car going south and one car going east. How quickly is this distance changing? It's the exact same thing we're talking about right now. Really. Just kind of bringing it back down to infinitesimal size, truly. So then what is this? How is this going to be? It's going to be equal to the square root of that squared plus that squared, which is what that is. So now I think about them truly as infinitesimal changes in length. So if I add all those up, I'm going to end up with the entire length. All right. Cool. That's it. That's about 3 times as much time I always want to spend on that. It's not a big deal. There is some homework with it, but it's just plug and chug. I'm not promising the integration will be easier, but that's fine because you need practice with that anyway. All right, that part I don't care about. All right, cool. Anything else from homework or anything? That's what we're all about today. Oh, real quick, before I forget, I didn't finish the 4D, but there is one point I want to make, so I just stopped it where you have to integrate it because 2 reasons. I ran out of room and I ran out of time. So I give myself like a 95 on this. But do you notice the limits on my integral there? Did anybody not get this, by the way? Anybody come in after I gave this out? Anybody else need a copy of that? And the answer key from last time? Okay. What are the limits on the integral?
Pi over 3.
Negative pi over 3. Pi over 3. But where were your... I don't know if you guys actually made it to that problem. I know at least one group in the back there did. But after I draw my... I did a decent job there. I tried to make one green so you could see it a little better. But you got this weird little dude here. Little butt there. Alright. And then the area you're trying to find is this crescent moon area. Right? So this here and this here, you can actually see it from my table I made. Once I added pi over 3 in there. You can see it from the table. Pi over 3 is 1.5 for both of them. But you can also eyeball it. This would be angle pi over 3, and that's the angle 5 pi over 3. But now watch, if you integrate from pi over 3 to 5 pi over 3, do you get this? No. Right? You guys with me? Because you actually are letting theta go this way. You've got to pick up the other stuff. So you want to go from negative pi over 3 to pi over 3 to pick up what you want to talk about over here. Does that make sense? You have to make sure that as you move from one limit to the next, in terms of your angle, that you're actually picking up the part of the graph that you want to talk about. So I can't say from 5 pi over 3 to pi over 3 either, because that would just be the negative of going this way. I need to go from negative pi over 3 to pi over 3, so it really does go from here to there. So that's one little thing you got to be careful about with these polar coordinates. It's kind of nice that there's a lot of different ways to identify an angle, but then it leads to stuff like this. Oh shit, there's a lot of different ways to identify an angle. I got to identify it correctly so I go the right side. So I actually pick up the area I want.
Can we also do from 0 to pi over 3 and just multiply it?
Yeah, like somebody said, I think it was your group that said, and this is beautiful, if you go from 0 to pi over 3 and then you can just double it because there is symmetry. You have to be certain that there's that right symmetry, but this is just a circle and a little butt graph. Those have symmetry. That's the technical term. The slang for it is the cardioid. Or maybe it's the other way around. It is a butt graph, yeah. Somebody argues it looks like a heart, but especially the way I draw it, it looks like it. So I'm sorry if that offends you. If you're offended now, you should have been offended a lot earlier. All right, is that cool? I just wanted to point that out. And I stopped early, but you should be able to integrate. You actually have to do the exact same thing I did in number 3. I end up with a sine squared in my integral, so I have to replace that using the identity, 1 plus. So on number 4, I end up with a cosine squared. I'm sorry, it was 1 minus an element. The cosine squared is 1 plus cosine of twice theta. You guys remember that? If I had, how do you integral of sine squared of something? You replace it with 1 minus cosine of twice the angle divided by 2, yeah. So if it was cosine squared, it would be a plus there. Cosine's the asshole, so cosine says, I get the plus. You get the minus sign. Or if you don't like to think of it that way, think of it a different way. I don't care. Right? We've talked about cosine being an asshole here, right?
Yeah.
Okay. Again, I told the same thing to my pre-calc students. Yeah.
Just want to check. So after you integrate that cardioid from pi over 3, then you subtract it from the integration of the
So
circle?
remember, the thing that's on there is, it's basically, this feels a lot like, now please, it's not this, and I almost don't want to bring this up, but you remember, do you remember washers? Discs?
Yeah.
Okay, all right. I know it's a bad time. But the one thing from that was relatively simple was r outer squared minus r inner squared. Does that remember? So this is really the same thing. So it's 1/2 r squared d theta. Well, I have an r inner and an r outer. So it's really the same kind of idea, right? So I put the definition of the circle, the 3 cosine theta would go here, minus 1 plus cosine theta there. So you're subtracting 1/2 r squared d theta, you're subtracting both of them. Does that make sense? So it is kind of like the washer. I was hoping it wasn't a dark time for you when you did washers.
That was terrible.
Normally that is a dark time for students, but I'm hoping that piece of it made sense. If you remember that r outer minus r inner, that should make sense. So it's really almost the same thing here. You can see how I set it up there on the answer key. So let me ask you, do you want to step through that problem a little more detailed, or you want to go somewhere else? You want to talk about something else? It's up to you guys.
I just have a quick question about
Yes.
next week. Are you going to have the Chapter 10 test back to us on Thursday so we can turn in corrections on it?
Oh, hell yeah. Yeah. I always give you the test back the next time I see you, right?
Yeah, I guess that's true.
Which you desperately should appreciate, and which will not hold true. I had a teacher that gave us our graded stuff back on the day of the final. Right, the first test he gave back to us finally. Right. How am I doing in the class? Don't worry, you're doing fine. No, how am I really doing? I don't know yet. He hadn't graded anything yet. I'm like, shit. Thanks, man. So I think because of that, I like to give you guys immediately, so you're not like, what the hell am I doing? What's happening to me? So what's up? What do you want to talk about? I don't want to.
I don't think you
we
want to
have
spend
very
too much
limited
more
time
on
today.
it.
Yes,
I
sorry.
don't think you want to spend too much more time on it, and I mean, there's other stuff to go.
Oh, it doesn't matter. So it depends on what you guys want to
Can
talk
we talk
about.
about converting Cartesian points to polar equations?
You can't convert points to equations. You can convert equations to equations or points to points
Okay.
all day.
Yeah.
Okay. Sorry, that's really weird looking thing. It's like something that belongs on an adventure. So converting, does it matter which way or both ways or
Just both ways.
what's the conversions for polar? You got to know these.
R squared equals x.
All right, cool.
X squared plus y squared. And then
All right, these should be the easy ones, right? This is what we've known since you learned trigonometry. If that happened. For some of us, somehow you're here and it didn't happen and I feel bad for you.
yeah,
Bless you.
You learn it in like SOHCAHTOA form, not that.
Oh, yes. So, Katoa, do you start to understand why I wish they wouldn't teach that? I don't know if you guys are with me on that yet or not.
Yeah, good.
Normally at this level you start to, some of you guys are like, I love my Katoa, don't you do it. All right, shit. But if you know sine likes y, cosine likes x, everything starts to make more sense. That's why I wish they would stop teaching SOHCAHTOA totally. Right, it's just like FOIL, really. Just repeat it. Okay, sorry. What else goes here? So this is how you go x from r theta and get to y if I have r theta. This is how I get r squared if I have x and y. How do I get theta if I have x and y? Tan theta. And again, another thing that we've known since we first learned trig, whenever that was. All right, cool. So if I had rectangular coordinates, and of course, well, let me give you one that's not nice. I mean, sometimes I'm going to make these so that they come out to an angle you know, which is when I don't want to see decimals. Okay. So, I don't know, let's do that, because that'll have a nice r, for example, but it'll have a gross theta. So what's, in fact, let's make this r. Add a negative, where, Jeff? There. Yeah. So the very first thing you should know going in, what quadrant are you in?
Second.
Yeah, so you identify that first thing. You're in the second quadrant, -4, 3, bam. Right? Sweet. And that's important because your inverse tangent will give you an angle that's related to your angle. It might be your angle if you're lucky, but we weren't lucky. We're in the second quadrant. It's not going to be your angle. So I don't know if you guys remember, inverse tangent comes out between what and what? What are the outputs?
0 and 180.
Negative pi over 2 and pi over 2.
That too, like a sine.
So, yeah, exactly. So how do I get, well, first let's start with r. How do I get r?
R squared equals x squared plus y
Yeah,
squared.
so r is the square root of x squared plus y squared.
I'm going to get 5.
What I love is when I have somebody tell me it's negative 16 plus 9, and you get some complex r, and then they put a question mark. You never covered this. Yeah, technically, you're right. Yeah, so that's positive 16, right? So r is 5, 3, 4, 5 triangle. Cool. So the r was nice, but our angle is not going to be nice. Theta will be the inverse tangent of what?
3 over 4.
Negative 3 over 4, yeah?
3 over 4.
That will return an angle that's in the, what do you think? What quadrant?
Fourth quadrant.
Fourth quadrant, because it's from negative pi over 2 to pi over 2. If it's negative, it'll give you something in the fourth quadrant. So that's the tangent saying, if it's negative, it's there. If you want in the second quadrant, you got to find the reference angle. You got to do the reference angle business. Are you guys still kind of with me? Some of you guys are looking at me like, I'm not really sure. So that, let me see. If I don't say, you can give me a decimal, but I don't care what you do, it's not going to be in the right place. What decimal do you get for that?
53.1.
All right, so that's degrees.
Yeah.
Maybe give me radians. Maybe give me radians. Please give me radians.
So the inverse sign represents like the opposite of the right angle. You know what I'm saying? Like
Not
it's
really.
tangent of that. Negative point, the inverse tangent of that would be like negative.
No. So remember, this means it comes from a triangle. It has an angle such that the tangent is 3, 4, and of course it's in the second quadrant.
Okay. So tangent would be 3 over 4, right? Oh, okay, never mind.
If you're trying to come up with a specific way to get a theta, you can't. You can't.
Negative 0.6435.
All right, cool. That's fine. So that's in the wrong quadrant. How do I get into the second quadrant?
Add pi over 2.
No.
No.
What's the period of tangent?
Oh, pi.
So add pi. Because really, think about it. I'm in the second quadrant. This is the angle we got. How do I get it back here? Pi minus, well, in this case, pi plus that because it's already negative, isn't it? So you add pi to it to get it to the right place. So now add pi and you get
2.4981.
all right. Blah, blah, blah. So then my point in rectangular it's negative 4.3. In polar, it's
5.
2.4981 roughly, approximately, right? Not negative, but approximately. How are we doing? And normally I like to make the angle come out nice for 2 reasons, so you don't have to worry about how many decimal places to take it to, and so I can continue to make sure you remember all your freaking trig value shit, right?
Yeah.
Because your Calc 1 teacher sometimes let you down. They should have been continuously making sure you remember your trig. If they should have remembered in Calc 2, you get a lot of trig. All right. If I was your Calc 1 teacher, I did not let you down. All right. Is that cool? And then the other way around is the reason I didn't do the other way around first is because the other way around is freaking easy as hell. And I have no qualm saying that. If they give me r and theta, r and theta, I'll give you that, sure.
Why?
Because the whole theme up here right now is decimals. If I gave you pi over 6, you could figure out what sine and cosine of pi over 6 is.
Right.
Right? But if I give you something you're not supposed to know, you can use your calculator. It's fine. I'll say something like round answers to 4 places or something. So how do you get x and y? What quadrant would this be in? What do I face?
Quadrant
First
3.
one.
I face pi over 12, which is in the first quadrant, but I go where?
Backwards.
So where am I?
3.
Third quadrant. I like it. So I know going in that I'm in the third quadrant. X should come out negative and y should come out negative. Just a little thing to know ahead of time. So what is x?
Negative 10.6.
But how do you set it up?
Oh, r cosine theta.
Yeah, r cosine theta, right? I mean, that's why that way is so freaking easy. If I give you polar, I don't care what the hell I give you, it's easy. I mean, period. Please let that be true. That's just true. So I can't even ask you to let it be true because it's just true. All right. And y would be negative 11 sine pi over 12. And you get, like Chris said, you get negative
10.625.
That makes sense. And then here's going to be smaller.
Negative 2.847.
847. Sure, sounds good. Is that cool? All right. What about equations? Because that was the other part of your question. I want to make sure
Yeah.
that this is something we want to talk
I
about.
feel like converting equations is harder. Maybe. I don't know.
All right. Yeah, the first one was Cartesian to a rectangular to polar. Points, yeah. And then we did polar to rectangular. Let that be simple. I can't make that simpler.
Because I was so good. It's too easy.
I know. Some of it really is.
I know for like converting equations, I think one thing that gets some people is that in parametrics you don't have to convert equations from.
Oh yeah, parametrics you solve for t, or you use identities or something.
But you don't have to convert from Cartesian to polar within the parametric.
Oh no, God no. You don't want me to do that. So if I add, now again, if I give you polar, it's normally much easier, but you gotta remember what you're looking for. And actually here it's about the same easiness. So if I see this, see if you guys can figure this out. Give you a freaky one. What's the true trig functions, or maybe even three? What three trig functions actually show up in my conversion equations? Cosine, sine, and tangent. Those are what I'm looking for. Do I see that?
Yes.
Not directly, but it is in there, right? So how do I make that show up?
One over cosine.
All right. Now, if you overthink this, which is really easy to do, you're going to do all the wrong stuff and go, what the hell's going on here? Cosine theta by itself is not equal to shit, because you can't say it's equal to x over r, because then that's mixing rectangular and polar. Does that make sense?
Yeah.
I want to replace all the polar shit with rectangular shit. I can't have any pieces of anything else left over. So it's not right to replace this with x over r necessarily, but that actually would get you somewhere confusing. So now, when I see cosine, what do I hope is with it? R, because if I saw r cosine theta, what would that be?
X.
X. So there's two kind of ways you could do this. One of them's a little bit better.
Can you multiply cosine theta?
You got the good way. What's up? Do it one more time. Yeah, so just multiply the cosine theta up. There's an r sitting over there waiting for him. He's like, come on up here, dude. You could have multiplied top and bottom by r, which would sort of suck. Because then r is the square root of x. I don't want to deal with that shit. So if you multiply the cosine theta up, you get r cosine theta equals 1. You get, what's r cosine theta? X. So when you're converting from polar to rectangular, you're looking for r cosine theta, r sine theta. If it's not there, you're either multiplying by r, or you're figuring out how to make it show up in some other way. You're also looking for...
The other way wouldn't be terrible, would it? Because you could divide by r.
Yeah, exactly. But you have to realize, you have to give it an r and then take it away. You have to realize that. And the brain sometimes balks at that.
Okay.
It's like, I just gave it to it. What are you doing? Right, but yes, you would still get there. So, what if I had this here? Well, this one's kind of evil, but I don't care.
Split it into a double angle.
How do you mean?
Two sines. Oh wait.
Yeah,
Is that squared or is that?
No, it's sine 2. Sine 2 theta. Because I don't have any conversions about 2 theta, do I? All my conversions are about theta. So the first thing I need to do, no matter what else, is I got to convert this to just talk about theta. Now here's where people trip up. And there's kind of an ugly part to this, and that's just, too bad.
R by 2?
Say again.
R over 2.
That won't be enough. Who needs an R? Who on this side needs an R?
Both of them.
He does and he does. So if I multiply by 1 R, one of them has to go without. And they can't break the R up and like eat it, so it's horrible little zombie trick function. Where did I go? So does that make sense? People start to distribute R, and I'm like, how the hell are you distributing across a multiplication problem? How the hell are you doing it? So you got to give that dude 2 R. So how many R's you end up with on this side? 3. So then this guy gets an R, this guy gets an R, everybody gets an R. You dick, look under your desk. There ain't shit down there. Get used to it.
Thanks, old bro.
Sorry.
Professor, I didn't get that part actually.
Sorry. So if I multiply both sides by R squared,
Okay.
can't I put one of these R's here and one of these R's there? Now, I'm going to do a problem down here that let me actually write it down. You ready? So this one looks familiar. I think I had one like this on another thing. You see how these are separated by a plus sign?
Yes.
Yes.
So how many R's do I have to multiply on both sides?
One.
Just one, because it will distribute to everybody.
Right.
It's sort of like the Jesus R. I have 1 R, and I don't know what religion you are. I don't care. Whatever your favorite deity is, right? Flying Spaghetti Monster says, "Here, have some of my meatballs." Like, I'm not sure how to take that, Flying Spaghetti Monster. It's just a little too intimate for me right now, dude. But you guys understand? There's 1 R, but it gets distributed because it's plus. This is not a plus. You can't distribute. You got 1 R, you got 1 R. So I need 2 because I got 2 people there that need an R, right? So then what's this side? This is the easier side. What's that?
2xy.
All right, so this
Or
is
2yx.
Yeah. Just to be specific, that's 2yx. Cool?
Yeah.
And again, alphabetize it. On this side,
R times x squared y squared, or plus y squared.
don't want any R's left.
Okay.
What's R by itself? It's the square root of this.
Oh yeah.
So what's R to the third? It's the 3/2 power of this. And if you want to, you can square both sides. Because technically you have to have a plus or minus there. I don't know if you guys were with me or not. You can square both sides so you get rid of that square root. So you get x squared plus y squared to the 3rd power equals 4y squared x squared. That's yummy.
Do you have any idea what that would look like?
Not really.
Okay. I guess I could put it in the fourth equation.
Well, if you go back to this, remember that's going to be a certain leave rows or something. I think they got into this book, didn't they? Can't remember all the little details. On this one, though, that's easier. You just multiply both sides by r, so you get r squared equals 5r cosine theta plus 2r sine theta. That's x squared plus y squared equals 5x
It's 4-leaf clover.
plus 2y.
4-leaf
Yeah, I
clover.
should remember which one was you double it. If it's even, you double it. If it's odd, keep it the same. I can't remember the one. Yeah.
On the
For the number of leaves.
On the previous answer, you took out the square of the y. Is that
Yeah, I
intentional?
squared both sides. So then
No,
it
but
became
the y
just
squared.
the 3rd power.
But the y?
Squared plus y.
Oh, sorry. Thank you. And what's this the equation of? Circle. I love it. I didn't say anything specific. Its center is somewhere, blah, blah, blah. Its radius is whatever, but it's a circle. All right, cool. All right. Good. I'm happy because I wasn't sure how this really quick way of doing shit would work. Yes.
On the group work, as far as the circle thing goes, I understand the general concept, but when it came to actually applying it and figuring out the formula further, I just...
Oh, if I ask you to find the center and the radius, you bring the pieces over, and the general idea is if you got pieces of x, oh yeah, Jeff, it won't work. If you got pieces of x, sounds like a pirate thing, but somebody's with me. Then you use completing the square to group them together. Because I know I want to get it in the form x minus or something squared, because that'll be where the center is now. So you have to use completing the square. Which I know you learn in algebra, but a lot of shit you learn early, you continue to use all the way through, right? So how do you do completing the square? Take half of this, square it. So add 25 fourths, so I better add 25 fourths to the other side.
25/4 because it's 5½ squared.
Yes, cool. So then you factor like 5. It's awesome. Cut that in half, that's how it's going to factor. Square it, that's what you're going to add. Cut it in half, that's how it's going to factor. Square it, that's what you're going to add. So I get equals 29/4. Is that cool?
Yeah.
So you guys did this, I remember. And then, so the center is going to be at 5/2, 1. And this radius is going to be root 29 over 2, because that's r squared, right? All right, cool. So then you can generalize something there as far as what your polar equation is going to look like and how it's going to translate your circle around, right?
Thank you.
Sure. See how the center was 5/2, 1, which is half of the coefficients of the original? Do you see that? You can start to make generalizations about what you see. Or not. Where do you want to go now? So this is just chapter 10, right? You guys are with that?
Yeah.
So it's going to be parametric calculus, polar calculus. And the polar calculus thing, we're going to focus on just finding areas, right? And I don't know if you guys probably don't.
Areas of like circles in a polar.
Well, like the area we did earlier with the crescent moon shape. Right?
Okay.
That's probably the hardest problem I would give you, that kind of problem there.
So integration.
Yes, I'm going to focus on the integration. They do also talk about, I think they talk about arc length in 10.4.
Arc length, parametric arc length.
No.
Okay.
Arc length is not a big focus for this course. It could be, but it's not for me. Yeah.
Like for that problem, if it's in decimal.
Oh, you mean these?
Yeah.
It's better to be fractional, believe it or not. Because decimal form, but for this, you could write it out all the way and you don't round. But if it was 29/9, then there's no way to write it and not lose something because it goes forever, right? I mean,
Right.
for 29/7 is even worse. So in general, I don't like decimals too much, right? It's better to have closed forms for things, yeah. Especially in Taylor series, right?
Exam Tuesday is going to be just 10, right? Section 10?
Yeah, just 10. Sorry I brought that up. There won't be any Taylor series on this test. I'm just saying. And don't forget also, just to let you know that I will have a practice final exam that I'll give
And a
you.
review.
Are we getting a practice test today?
No, it was this. It was the group worksheet. Yes.
Okay.
You said there was an answer key to the group worksheet?
Yes, there is.
You may have.
Does anybody else need one? Okay. Oh shit.
Oh man, still other copies, aren't fancy.
Dude! Yeah, look at that. Trying to like the little butt dude in green, just so he'd stand out a little bit against the circle.
Well, it's appreciated.
I tried. It took me a long time to do all these by hand. No, I'm kidding. Color printers are awesome when they work.
When they work, yeah.
With mine, it's, who knows. Gonna work today? Really? You are? Oh, wow. It's like, oh yeah, it wasn't supposed to work.
I think you're sick.
So it's
supposed to start raining any second.
This, right?
Huh?
Polar graph, or we have to bring one.
No. I'll provide you with
Okay.
any graph stuff you need. I'll provide it.
Just in case.
Unless you have one you like better, you can bring it. I'm not going to make you use mine, but it will be available.
Okay. Sure.
So just like on the little parametric sheet we had, I gave you the little
Yeah.
rectangular,
Right.
But again, if you'd rather use your own graph paper, please do. I don't need you to use mine. It's all right. Just don't use non-line paper. If you're turning homework in and you did all your polar graphs on like a notebook piece of paper, you're going to do it again, or just not get points. Either way. Some of you guys say, "Oh, this is a harsh reality." I told you. Google now. Google image search. Get the polar coordinate paper, and you got to do it on there.
Is that going to be 10.3 and 10.4? Somewhere?
Wherever it asks you to graph. Yeah, 10.3 for sure. 10.4, I think sometimes they'll ask you to graph and then find the interval. Yeah. Trust me, notebook, there's no way to identify where pi over 6 is exactly, unless you got your little protractor out. I don't know if anybody's, let me get my protractor. If you're doing that, shit, just print out some freaking polar graphic. My God. I really doubt you're doing it, though. Yes, sir.
Can we do a problem up to 4?
Yes.
It's off web design. I don't know what problem is that we're doing.
Sure.
But it's r squared equals 72 cosine 2 theta.
R squared equals.
What number is this? It's number 5. 110.2. 74. But it's off web design. Right, I do web design.
R squared equals
72 cosine 2 theta.
72.
Yeah. I don't know what design gives this number. And r equals 6.
And then what's the question?
And it says find the area of the region that lies inside the first curve and outside the second curve.
Ooh, I like it. So what's this going to be the graph of?
Circle.
I love it. Radius equals 6 is the definition of circle centered at
0.
0, 0 with a radius of 6. So that's going to be 1, 2, 3, 4, 5, 6.
See,
For
you
me,
can
that's
do
good. So there it is. Huh?
You can do it. You can do it.
I can do it. Let's see. If you really loose definition of circles, then I have done it. Okay. This guy, what do you think? I mean,
Also a circle?
now watch. The largest cosine can be is,
2. No, 1/2.
that's neat. The largest cosine of anything can be is 1, thank you. Right? The largest cosine can be is 1. You with me? I don't care what the hell's on the inside. The output can be 1. So the largest the side can be is 72, and the square root of 72 is 6 rad 2,
Oh, yeah.
which is like 8.4, roughly. So I need to go out a couple more places. But when you graph this, and again, if you, and this is r squared, right? And they do have, I want to point this out, I think it's in 10.3. They do have some examples. Yeah, here we go. Sort of. Hey, there we go. Example 8 on page 658 is exactly what we're dealing with here, just with an amplitude of 1. You guys kind of with me? I mean, that's what I do. If I'm a student in a math class and I got a problem and I'm not really sure what's going on, I look for an example that's sort of like it. Well, there's an example that's almost exactly like it. So I know what the shape is supposed to be. It's supposed to be a 4-leaf clover, right? And then you can make a wish. But like at 0, it's going to be the biggest output. You with me? So at 0, it would be 8.4. So that's 6, 7, 8, 9. There's 8.4. And then it's going to be just a really quick and ugly, dirty. Dirty. Yeah. It's going to be something like that. Holy crap and a half, Jeff. You tried.
The left one is really big too, isn't it?
You tried. Huh?
The one on the left's really big too.
Oh, look at that. Holy crap. I forgot about my scale. It's the Popeye clover, right?
So it's supposed to go all the way, right?
Yeah, it's supposed to be that big also on that side. Now it's even bigger on that side. But anyway, this is a lot like the one we did earlier with the circle and the butt dude. And we had to find this area here. So you want to figure out, and do they give you any, is that all they say? What do they say?
Yeah, it's just that.
What does it say again? It says find the area.
Of the region that lies inside the first curve and outside the second curve.
Oh, inside the first and outside the second. All right. The first curve was a circle.
No, that was the second one.
Oh, the second one. Okay. So inside the first, but outside the second. Oh, so cool. So here's what you do. If you could find out this, you would multiply it by how many times it shows up.
4.
Right? Does that make sense? So now what you got to do is you got to figure out, that seems to be an important point. Right? Because that's going to be where it goes from this to this being the outer limit. Does that make sense? All right. I'm sorry I'm rushing, but I'm basically out of time. You want to find that intersection point. And you got to be careful too. There is something about that square there that's going to, I can't remember, I don't think it's going to mess you up. Thank you. Just double check. You can plug this in your calculator too. You can put R1 as plus 72 square root and negative 72 square root plus 72. Just to make sure about the shape. All right. But you find that, so you want to integrate from 0 to this, right? Where, and actually that's, oh yeah. And then you want to integrate, at some point this goes to 0 here. So if you integrate from 0 to this, you'll pick up that area. And then how do you get this area? It's going to be the whole area of this minus, let's see, how do I want to set this up? Minus this somehow. Yeah, it's interesting. So you want to go from this to this. So you want to subtract, which way you want to go? Wait a minute, this is easier than I thought. I'm being silly. From this point, you just integrate this guy. So if I had just a clover, just this thing here, find that area, I just got to integrate from this angle to that angle, this. Now for this, it's not the whole clover, is it? It's the circle, it's the clover minus the circle. Or it's actually just the part that's in the circle. And I'm making this harder than it needs to be. And you're all like, yeah, you do that a lot, Jim. Yeah. I'm trying to rush. At this point, it's easier. I'm assuming what they wanted the problem to be, but this problem is a lot easier than I thought. This is the point where you integrate, on one side you integrate the clover, you integrate this dude, from this angle to this angle, where it comes back to 0, and it's going to be pi over 2, more than likely, or something like that, pi over 4. And on the other side, you're integrating this from 0 to that, because that's just the circle there, right? So I don't want this whole clover piece. I want what's inside the circle. So I just got to integrate the circle from there. All right, that's it. I don't know if you got anything from that. Yeah. Okay, thanks. All right, guys.
No.
So Tuesday I'll be in the office starting at 11 if you want to come earlier.
That you integrate and then you subtract.
So we guys do anyway.
And the other one.
You
I thought
correct
you said
the grade 11
when I broke it
grade
down,
number 5.
it was
No.